Our comprehension of science is vast. Given precise data on the forces at play, I could accurately predict the trajectory of a ball tossed into the air. Through the lens of chemistry, science unravels the molecular composition of that ball. We can even forecast the sound it will produce upon landing. Much like a candle piercing through darkness, science sheds light on our understanding of the world. However, there are limits to this illumination. Despite our extensive knowledge, there are still enigmatic realms waiting to be explored. There are questions unanswered and perplexing results that challenge our certainties. Certain experiments hint at the possibility that our perception of reality may be flawed, raising existential inquiries. Are we truly real? Is time as linear as we assume? These uncertainties invite us to confront the unfamiliar edges of our comprehension. If you're prepared to confront these uncertainties head-on, I present to you a series of experiments. Consider this your cautionary warning. Interestingly, most of these experiments revolve around the peculiar nature of light. Despite its apparent simplicity as a conveyor of energy traversing the cosmos, light remains profoundly mysterious. While it aids in perception and sustains life on Earth, its true nature eludes easy comprehension. When scientists delved deeper into the nature of light, they encountered unexpected complexities. Notably, the double-slit experiment revealed that light exhibited wave-like properties, challenging previous assumptions about its particle nature. Fast forward to the early 20th century, and the discovery of the photoelectric effect introduced another layer of intrigue. It appeared that light behaved as discrete packets of energy, or photons, complicating the understanding of its dual nature. Revisiting the double-slit experiment with modern techniques uncovered even more paradoxes. When observed closely, light behaved as particles, yet it still produced interference patterns characteristic of waves when not directly observed. This duality confounded scientists, suggesting that light operates not as a fixed entity, but rather as a probabilistic wave. When probed, it manifests definitively, but in its unobserved state, it exists in a state of uncertainty, simultaneously occupying multiple states. In essence, light presents itself as a paradox, challenging conventional notions of reality and perception. This enigma underscores the intricate relationship between observation and reality, hinting at the profound mysteries yet to be unraveled in the realm of physics. These lenses function by consisting of slender chains of molecules aligned lengthwise across the lens. Light oscillating in alignment with these molecules gets absorbed, while light perpendicular to the chains can pass through unimpeded. However, the intriguing scenario arises when a single photon encounters an orientation diagonal to the lens. In this instance, the photon doesn't partially pass through. It seems incapable of absorbing only the portion oscillating parallel to the lines, while allowing the perpendicular part to pass through. Instead, the photon abruptly aligns itself with either orientation. It either gets fully absorbed or passes through entirely, but now with a new perpendicular polarization to match what would facilitate its passage through the lens. How do we ascertain that the photon wasn't initially oriented this way? Consider what happens with additional lenses. When a second lens is positioned behind the first, the light can be entirely blocked out if the two polarizations are perpendicular. If we rotate the second lens 90 degrees relative to the first one, any light passing through the first lens has zero chance of passing through the second. This results in total darkness. However, adding a third lens and placing it at a 45-degree angle between the other two leads to an unexpected outcome. Light begins permeating through all three lenses again. While this may seem counterintuitive, it actually disproves the notion of light having a fixed orientation. At each new lens, it seems to snap into focus, determining whether it was oriented correctly all along through a probabilistic roll of the quantum dice. For instance, if the photon successfully passes through the first lens with a 50% chance, it's due to its perpendicular alignment with the lens polarization. As it encounters the second lens, it approaches from a diagonal polarization, resulting in another 50-50 chance of passage. This probabilistic process repeats with each subsequent lens, culminating in a final 50% chance of passage through the third lens. Although not all photons navigate through all three stages successfully, only around 12.5% do. This percentage is significantly higher than zero, unlike the scenario with just two lenses. Light seems to adhere to discrete quantities, behaving quantumly by snapping to a definitive value upon observation, yet retaining a probabilistic existence otherwise. This phenomenon bears resemblance to harmonics on a bounded string, where only specific wave patterns are permissible. Light, it appears, operates similarly, yet the mechanisms driving this behavior remain elusive, leaving us pondering the fundamental nature of reality and the universe's penchant for probabilistic uncertainty. You can also consider a wavefront velocity, which denotes how swiftly the Lad photon in a group of photons can move. The terminology might seem dense, so let's simplify it with an analogy. Imagine a stadium full of people performing a Mexican wave. The motion of the wave created by the people represents the phase velocity. You can observe this wave propagating through the crowd, seemingly traveling fast. However, the crowd itself isn't progressing anywhere, so the true speed of our wave is zero. The individuals within the crowd represent the group velocity, or perhaps the wavefront velocity. Now, envision if we wanted to mobilize our crowd to march while still doing the Mexican wave. They could do so, maintaining the wave as they move. Yet, despite the apparent rapid movement of the wave's peaks in the direction of their travel, it would dissipate upon reaching the front of the crowd. Information exchange couldn't exceed the walking speed of the crowd, irrespective of how swiftly the wave peaks appeared to move. In relativity, Einstein never argued that the phase velocity couldn't surpass the speed of light. His assertion was that information couldn't travel faster than light. Thus, if you attempted to convey a message by sending a group of Mexican wavers towards someone, the speed of their waving becomes inconsequential. Until the initial person in the group reaches the destination, no information can be transmitted. Nonetheless, this distinction between the waves within light and the speed of light itself becomes intriguing in our subsequent experiment, where things take a peculiar turn. Now let's revisit the double-slit experiment. Traditionally, researchers examined how light can exhibit both wave-like and particle-like behaviors. However, in 2023, scientists from the Imperial College devised a method to separate the slits in this experiment not spatially, but temporally. They achieved this by utilizing a transparent material called indium tin oxide, which under specific conditions can transition from transparent to reflective. This material is commonly found in mobile phone screens. By firing a laser at it and swiftly altering its transparency, they created a narrow time window termed a time slit. When they sent two laser pulses through these time slits in rapid succession, an interference pattern emerged. This pattern, however, differed from the traditional 3D space double-slit experiment. It affected the laser's frequency. To visualize this phenomenon, let's depict the experiment in terms of time. We can represent it on a 4D graph, where space is along the x-axis and time is along the y-axis. The photons leave the emitter, hit the time slit, get reflected, and reach the receiver. A second photon is released later, arriving at the receiver at a slightly later time. If light behaved conventionally, traveling at its usual speed, this would be the end of the story. However, the interference pattern suggests that light is traversing paths through time, occasionally even seemingly backward. This mind-bending result, observed by a research team at the Imperial College in London, has startling implications. It indicates that light always chooses the path of least time, attempting various routes, including those through time itself, to optimize its journey. Though we never directly observe photons taking these alternative paths, interference patterns suggest their existence. This departure from conventional understanding challenges our perception of causality and linear time. While it may seem improbable for information to travel backward in time, quantum phenomena hint at such possibilities. Despite the resulting paradoxes, on the quantum level, information appears to defy the unidirectional flow of time. I grasp the perplexity of the situation. It defies intuition and appears implausible by all conventional measures. In previous discussions, I emphasized that objects would necessitate infinite energy to approach the speed of light. So, how could something move so swiftly as to reverse the typical progression of time and arrive at a destination not merely instantaneously, but before its departure? Even light, the swiftest entity we know of, cannot accomplish this feat. Yet, this constraint concerning the speed limit of causality seems to apply primarily to the macroscopic universe, everything significantly larger than an atom. However, on the quantum level, time may adhere to different principles, or at least the velocity of causality comes with notable caveats. To illustrate this notion, we delve into the realm of quantum entangled particles, attributed to the insights of John Stuart Bell. I must forewarn you, what I'm about to unveil may challenge your understanding of causality. Now, what exactly are quantum entangled particles? In the realm of quantum physics, it's feasible to collide two particles in such a manner that they become intricately linked. Consequently, by measuring the properties of one particle, you gain insights into the properties of the other. For instance, if the initial total momentum of these particles was zero, observing the momentum of one particle determines the momentum of the other, ensuring the conservation of total momentum. This principle extends to various other particle properties, such as position, polarization, or spin. Initially, this concept may seem innocuous, akin to friends agreeing on plans for an evening out. However, there's a twist. Contrary to what Einstein envisioned, it turned out that the particles didn't pre-establish their properties. Strangely enough, they still consistently align with each other's measurements, regardless of distance. This enigmatic phenomenon of quantum entanglement challenges our conventional perception of fixed particle properties. Our penultimate mind-bending experiment reveals that particles only manifest properties upon detection. It's reminiscent of the double-slit experiment, which focused on the position of photons. Similarly, particles exhibit a certain vagueness regarding their properties, relying on probabilities defined by quantum wave equations. The Bell experiment, named after its originator John Stuart Bell, delves deeper into this conundrum. Bell sought to discern whether particles possessed hidden variables, secret properties predetermined before measurement, or if they improvised their attributes upon measurement. He made a shrewd observation regarding the spin of particles. Quantum spin, despite its name, pertains to a particle's response to magnetic fields rather than literal spinning. Quantum entanglement entails that if one entangled particle's spin is measured in a given direction, the other particle will exhibit the opposite spin in the same direction with certainty. Bell devised a clever question to probe this phenomenon further. What are the odds that the spins of two entangled particles measured in randomly selected directions match? Classical physics posited that particles harbored predetermined spin values, leading to specific predictions. Yet experimental outcomes favored quantum physics, which asserted that particles improvise their spin values upon measurement. This discrepancy underscored the mysterious nature of quantum entanglement, where information seemingly transcends space and time boundaries, operating at speeds exceeding that of light. The ramifications of these findings are profound, challenging not only our understanding of reality, but also suggesting the existence of phenomena that defy our traditional notions of causality. This revelation invites further exploration into the fundamental nature of light and its decision-making processes, as exemplified by the delayed choice test, our final experiment. And with that, drop your thoughts about this video in the comments below, and don't forget to like and subscribe, and we see you in the next video.